Hey everyone, Mr. Hauk here. In today's lesson, we're going to continue simplifying trig expressions using a variety of different identities and formulas. Okay, so in the previous lesson, we started simplifying trig identities, or trig expressions rather, but we were only using the reciprocal and quotient identities, and I think we even used some even and odd identities here and there. Today, we're going to continue simplifying trig expressions, but now we're going to throw in the ever-important Pythagorean identities and its variants. Okay. A few lessons ago, we proved these Pythagorean identities, and we saw that each Pythagorean identity can have two variants based off of how you rearrange the equation. So let's just keep those in mind. But let's go ahead and get started here. Let's start with us trying to simplify secant theta minus sine theta times tangent theta. And remember, our goal is we want to simplify these down to either one trigonometric function or a numerical answer, or which means a constant. Okay, so starting here. So we're starting with secant theta minus sine theta times tangent theta. And what I'm going to go ahead and do is, just like in the previous lesson, I'm going to start decomposing things into sines and cosines. So I can see that the secant theta is going to be a 1 over cosine, and this tangent theta is going to be a sine over cosine. So that's the first thing I do. I decompose into sines and cosines. Now, notice that sine theta times sine theta, that's going to be sine squared of theta. And also notice that both of these have denominators of cosine, because 1 times cosine is just going to be cosine. So since these have the common denominator already of cosine, I can combine the numerators. So this is going to be 1 minus sine squared of theta over cosine of theta. That's kind of what we're leading into here. So that's what this simplifies to. Now, this is where we have to think about anything that simplifies. Well, notice that we have this 1 minus sine squared of theta. Well, if we look at our Pythagorean identities, I have a sine squared of theta right here, and I have a 1 right here, and notice if I subtract the sine squared of theta to the other side, I get cosine squared of theta equals 1 minus sine squared of theta. So this 1 minus sine squared of theta is really a cosine squared of theta. So that's everything that I put right here. So let's replace this with a cosine squared of theta. And now notice, well, remember, cosine squared of theta really means cosine theta times cosine theta. And one of these cosine thetas will cancel with the cosine theta in the denominator, and all we'll have left is cosine of theta. All right, so it's a really good example of using the Pythagorean identities to help us simplify an example. So let's try another one here. Next, we want to simplify cosine x times secant x minus cosine x over secant x. And in a very similar fashion, I'm going to continue decomposing things into sines and cosines. So secant x is going to turn into 1 over sine of x, 1 over cosine of x. And this secant x is also going to turn into 1 over cosine x. So that's the first thing I did there. Now notice that, in this piece right here, this cosine x times 1 over cosine x, well, cosine x and cosine x will cancel to give us 1s. So this whole thing is really just going to be a 1. And then with this piece, the cosine x over 1 over cosine x, I'm going to go ahead and do keep, change, flip. So that's what I've done so far. This piece turns into a 1. This piece, I've done the keep, change, flip. Notice the cosine of x, that's right here. Notice that I've written it as cosine x over 1, just to represent it as a fraction. The division gets changed to a multiplication, and then the denominator here gets flipped upside down. 1 over cosine x turns into cosine x over 1. And we can see here that cosine x times cosine x, that's going to give us cosine squared of x. So this is going to simplify to 1 minus cosine squared of x. And then, again, especially the fact that we have the squared here kind of tells us, it hints to us that we're going to use a Pythagorean identity. And if we look up here, if I go ahead and subtract cosine squared x and get the sine squared by itself, then I get sine squared x equals 1 minus cosine squared x. So that's what this 1 minus cosine squared x will be equal to. It's going to be equal to sine squared x, which is our final answer, because the entire 1 minus cosine squared x is sine squared x. Okay? So two really good examples, and both of them featured Pythagorean identities, or variants of them at least. Right? Continuing, let's try example 3 here. And just like in the previous notes, you can expect that some of these start to kind of kick up in difficulty in terms of what you're going to have to be able to do to solve them, or simplify them rather. So start to kind of anticipate that as these examples go along. But here we're starting with secant squared alpha over secant squared alpha minus 1. And one thing that you want to be a little hesitant on is, when I look at these pieces, over the last several examples, we've gotten used to decomposing everything into sines and cosines. We'd probably look at the secant squared theta and probably want to immediately turn it into 1 over cosine squared, or look at this and maybe want to immediately turn this into 1 over cosine squared. But we actually don't want to do this in this problem, because notice this is a secant squared alpha minus 1. And when you see this, when you see a secant squared and you see a minus 1 with it, one thing that should really be jumping into your mind are the Pythagorean identities. Because look at it right here. If I took this 1 and subtracted it to the other side, secant squared of theta minus 1 is really equal to tangent squared of theta. So that's what I end up doing right here. Secant squared of theta minus 1 equals tangent squared of theta. And I should really be saying alpha. The angle we're using here is alpha. Doesn't really make a difference though. So I'm going to go ahead and replace secant squared of alpha minus 1 with tangent squared of alpha. And I'm leaving the numerator as secant squared of alpha for right now at least. Okay. At this point, I think it's a good idea to start turning things into sines and cosines. So secant squared of alpha, that's going to be 1 over cosine squared of alpha. And tangent squared of alpha is going to be sine squared over cosine squared. So that's our next step right there. Decompose into sines and cosines. And once we're at this point, I think it's pretty easy to see that we're going to want to do the whole keep, change, flip business. So keep the top part, 1 over cosine squared of alpha, change the division to a multiplication, and flip the original denominator, sine squared alpha over cosine squared alpha, flip it to cosine squared over sine squared. And this is what we get as a result right here. Notice when we start to simplify, cosine squared alpha and cosine squared alpha will cancel. We're going to get 1 over sine squared alpha. And we know that 1 over sine is cosecant, so 1 over sine squared alpha is going to be cosecant squared alpha. And that's going to be our simplified version. So again, a really good example of using Pythagorean identities and really looking for opportunities to use them, such as when we see this, secant squared with a minus 1. Really hints to us that we want to use the Pythagorean identity. All right, so now we hit example 4. Tangent theta plus cotangent theta over cosecant squared theta. And again, I want to think about, when are good times to use Pythagorean identities and when are bad times to use it. And I look at this cosecant squared theta, and this is actually not a good time to use a Pythagorean identity, mostly because we'd be making the problem harder on ourselves. If we go and look at cosine squared of theta, well, cosine squared of theta is 1 plus cotangent squared of theta. But putting a 1 plus in this denominator, rewriting it as 1 plus cotangent squared, is just going to make the problem harder on ourselves. So what I think is a good idea here is to decompose into sines and cosines again. I think it's a really good first step. So that's what I did first. Tangent of theta, I decomposed to sine theta over cosine theta. Cotangent theta, decomposed to cosine theta over sine theta. And cosecant squared, decomposed to 1 over sine squared. So now at this point, one thing that kind of jumps out to me when I'm looking at this is I see a fraction being added to another fraction. And automatically that says to me, we want common denominators. So this is going to look a little weird because this has a denominator of sine of theta. This has a denominator of cosine of theta. Well, to get common denominators, the common denominator is going to be cosine theta, sine theta. So what that means is this piece is going to have to get multiplied by sine theta over sine theta. And this piece is going to have to get multiplied by cosine theta over cosine theta. And it's because you can see that they're going to have the same denominator after everything is said and done. So that's what I do in my next step. Multiply this by sine theta over sine theta, multiply this by cosine theta over cosine theta. And what's going to end up happening, if we kind of look ahead to see what it's going to result in, we have a sine theta times sine theta, which is really sine squared. And we have a cosine theta times cosine theta, which is really cosine squared. So, again, sine squared, cosine squared, and I'm adding them together because they both now have the same denominator of sine theta times cosine theta. And this denominator over here, the denominator of the overall fraction, still a 1 over sine squared. So here's where we can start to think about using identities. I can really make this numerator easier because I look at sine squared theta plus cosine squared theta, and I notice that's just equal to 1. So I'm going to go ahead and replace this entire piece, the sine squared theta plus cosine squared theta, I'm going to replace it with a 1. And now the problem is starting to look significantly easier. I'm also noticing that this is going to be a good opportunity to do the keep, change, flip stuff. So I keep this numerator, 1 over sine theta cosine theta, change the division to a multiplication, and flip the denominator to sine squared theta over 1. By the way, this is a sine squared. I know it might almost look like a sine 2 theta. This is a sine squared theta. Okay, I should have written that a little bit higher there. But either way, sine squared theta is really sine times sine. And one of these sines is going to cancel with this sign right down here. Meaning all I'm going to have left over is sine theta over cosine theta. And we all know that sine over cosine is tangent, which is our simplified version of this answer. So this problem was pretty involved. A lot of fractions. You had to get some common denominators. You had to apply a Pythagorean identity right here. So a very good example of a lot of skills being used in one problem. Okay, if you need to go back and watch that again, I strongly advise it. And for our last example, this one is not so much difficult, but it is going to be a tedious problem because there's going to be a lot of foiling is what's going to happen here. So we want to simplify 4 cosine x minus 3 sine of x squared plus 3 cosine x plus 4 sine of x squared. And we all know these squareds mean really that we're multiplying this times itself plus this times itself. So if I go ahead and write all of that out, this is what I end up getting. So here's this term times itself plus this term times itself. And let's start this algebraic process of foiling these expressions. So first thing I'm going to get, and I'm looking at this chunk first, so let me kind of zoom in on this. First thing I'm going to get is 16 cosine squared x, because it's 4 cosine x times 4 cosine x. So of course the 4 times 4 gives us the 16. The cosine x times cosine x gives us cosine squared x. So that was first times first. Now we're going to do outside times outside. And that's going to give us minus 12 cosine x sine x. So again, 4 times negative 3, there's your negative 12. Cosine times sine, well, just cosine sine. Then inside times inside, it's going to give us another negative 12 cosine x sine x. And then last times last, well, negative 3 times negative 3, that's going to give us the positive 9. And then sine times sine is sine squared. So this whole mess right here, coming from the foiling of this piece. Now we need to foil this, and we're going to do it the same way. 3 cosine x times 3 cosine x, that's going to be 9 cosine squared x. Go back. 3 cosine x times 4 sine x is going to be 12 cosine x sine x. 4 sine x times 3 cosine x is going to be 12 cosine x sine x again. And then lastly, 4 sine x times 4 sine x is going to be 16 sine squared x. So a lot of pieces. Notice it took me all the way across the page to write all that out. But some really cool stuff happens here. We have a negative 12 cosine x, a negative 12 cosine sine x, negative 12 cosine x sine x. But then we also have a positive 12 cosine x sine x and a positive 12 cosine x sine x. So these are all going to cancel each other out. Now we just really need to look at the like terms. Notice we have a 16 cosine squared x and a 9 cosine squared x. That's going to give us 25 cosine squared x. And then we have a 9 sine squared x and a 16 sine squared x. That's going to give us a 25 sine squared x. So all that mess simplifies into this. And if you look at these pieces, they both have a 25 in common. So let's go ahead and factor the 25 out. If I factor 25 out of 25 cosine squared x, we just get the cosine squared x. If I factor the 25 out of 25 sine squared x, I'm just going to get the sine squared x. However, cosine squared x plus sine squared x is equal to 1. So this whole thing is really just a 1, and 25 times 1 is just 25. So really tedious problem, a lot of multiplying, a lot of combining like terms, but a pretty cool problem nonetheless. So again, as you can see in every single one of these examples, very similar to the examples that we did yesterday, only in each one of these, you saw a Pythagorean identity get used somewhere. Whether it was at the beginning, towards the end, every problem had one of these Pythagorean identities in it. So pretty cool. In the next lesson, we're probably going to continue to expand our toolkit. We'll probably start simplifying using the sum and difference formulas and the double angle formulas. And all this is kind of leading towards trig verifications where we start proving statements. Okay? See you in the next one.